Guess what? We made it to chapter 5. It's time for section 5.1. This is on estimating with finite sums. So in this set of videos, we're going to see accumulation problems as area. We're going to see the rectangular rectangular approximation method. A mouthful. Abbreviated RAM. Thank goodness I don't have to say that again. In video 3, we'll talk about volume of a sphere. And we may leave the fourth subsection, cardiac output, for another day. In this video, we're going to see accumulation problems as area. Notice there's no new definition. There's no new rule of theorem. But what we will see is a lot of thought processes, a lot of metacognition with what we've learned so far from calculus and how we can extend that in a new line of thinking. So let's start with what we know. We know why a scientist pondering motion problems might have been led to consider slopes of curves. Why is that again? Oh, right, because slopes of curves talk about an instantaneous rate of change, which has a direct link to motion problems. But what do the same motion problems have to do with areas under curves? That's what we're going to be thinking about from now until the end of this semester. Areas under curves. So consider the following problem from a typical elementary school text. It starts like this. A ship moves along an ocean at a steady rate of 7.5 nautical miles per hour, also known as knots, from 7 a.m. to 9 a.m. What is the total distance traveled by the ship? Well, we know that famous formula, distance equals rate times time, or D equals RT. And we can use that pretty simply to figure out the distance by multiplying the rate, 7.5 knots, times the time. In this case, 7 a.m. to 9 a.m. is 2 hours. And that's going to give us 15 nautical miles. Nautical miles. So that's simple, but how is this connected to the graph of a velocity function? How is this calculus? Well, let's find out. You might notice that the distance traveled by the ship, 15 miles, is exactly the area of the rectangle whose base is the time interval 7 to 9. Remember, we started at 7 a.m. and went to 9 a.m., the ship traveling, and whose height at each point is the value of the constant velocity function 7.5. Take a look at the graph below. So see on the x-axis, or in this case, the h-axis, we have time equals 7 a.m. and time equals 9 a.m. there. So the base of this rectangle is 2. Then the velocity function was constant, right? So it's a horizontal line when we graph it. Velocity in miles per hour, 7.5. So that means the height of this rectangle is 7.5. So the area of the rectangle is the height, 7.5, times the base, 2, and that's 15. Just as the total distance traveled, distance on the last screen was equal to the rate, 7.5, times the time spent traveling, 2. So again, 15 nautical miles. It's no accident, since the distance traveled and the area are both found by multiplying the same two numbers together. Let's move on. That same connection between distance traveled and rectangular area, this is a big deal. There's a connection between distance traveled and rectangular area. That connection could be made no matter how fast the ship was going or how long or short the time interval was. But what if that ship had a velocity that varied as a function of time? In other words, the velocity is no longer just a horizontal line, but the velocity is a variable function that moves up and down, kind of like the graph you see here below. That graph would no longer be horizontal line, so the region under the graph would no longer be rectangular. What does that mean for us? And is the connection still there? Would the area of that irregular region still give us the total distance traveled over the time interval? Well, some important guys, Galileo, Newton, and Leibniz. You've heard of them all before. They all thought that it would. And so there was this tremendous interest throughout the 1600s in finding the area under curves. Big deal. Area under curves. Again, that's what we're going to focus on for quite some time. Those scientists imagined that the time interval partitioned into many sub-intervals, each one so small that the velocity over it would essentially be constant. What do we mean by that? Take a look at this. Geometrically, their idea was to slice the irregular region into thin, narrow strips. Each of those strips would be nearly indistinguishable from a narrow rectangle. So rather than trying to find all of the area at once, they said, let's take a look at subintervals or small regions. If we slice the region up into these small strips, that small strip is barely different than the rectangle that could be drawn around the same place. And since we know how to find the area of a rectangle, we could find the area of each of these thin little rectangular strips, add them all up, and we would have essentially a really good estimation of the area under that curve. Like we saw a while ago, if we have the area under the curve, we have total distance traveled. So let's move on from here. Finding the distance traveled when one knows the velocity at each instant of time is a process of accumulating distance. That's what we would do. We would find the area of the first rectangle, the second one, the third, the fourth, and we would add each one successively until we had the entire region worth of thin strips. Adding those all together would give us an approximation of the distance traveled over that short period of time. So there it is. The area of each narrow rectangle is an approximation to the distance traveled over that short period of time. Other accumulation problems can be viewed as areas. So here's our first example of how this might work. Consider a snowstorm that starts at 3 a.m. Over the first 2 hours, the rate of snowfall increases from 0 to 1.2 inches per hour. For the next 3 hours, it continues to fall at 1.2 inches per hour. At 8 a.m., it begins to taper off, decreasing at a steady rate until the snowfall ends at 10:30 a.m. Our question: find the total amount of snow that falls during the storm. So what we want to do here, before I start crossing everything out, let's highlight it. Find the total amount of snow that falls during the storm. So no, we're not finding total distance traveled, but yes, we are accumulating all of the snow that fell. It's still a rate times a time, or at least that's what we're looking at in terms of the graph. Notice that on the x-axis, we have time. On the y-axis, we have a rate. This is the snowfall rate, 1.2 inches per hour. Notice then that the graph in blue is exactly what was given to us in the words of the example. Over the first 2 hours from 3 a.m. to 5 a.m., the snowfall steadily increased until it was snowing at 1.2 inches per hour. For the next 3 hours, the snowfall was steady, 1.2 inches per hour the whole time. And then finally, from 8 a.m. until about 10:30 a.m., the snowfall gradually and steadily decreased until by 10:30 a.m. there was no more snow. So our task here is not much different than the task of figuring out the distance traveled by the ship traveling at 7.5 nautical miles per hour for 2 hours. We still want to find the area underneath this curve, and that can be done many different ways. I think it's probably most natural to take a look at the area as a broken up triangle, rectangle, and third triangle. So let's do that first. So we'll say the area, which is also the same as the snowfall. We'll say total snowfall would be this. So the first triangle has a base of 2 hours and it has a height of 1.2. So 1.2 times the base 2 times 1/2. So there's your triangle area, plus the next rectangle has a base that goes from 5 to 8. So it has a base of 3 and it has a height of 1.2. And then the last triangle has a base not of 2 like the first one. This one has a base of 2.5. 2.5 times its height of 1.2 times a half because it's a triangle. And all together, this should come out to be about 6.3 total inches. And so there we have it, an accumulation of areas. Now, this was one way to do the area. We could have done this a few other ways. We definitely could have taken the whole entire shape as a trapezoid and looked at it that way, where it had a height of 1.2, one base of 3, and another base of 7.5. We also could have done like we saw in the previous setup, cut it into thin strips. Maybe those strips were one every hour. So we had a triangle, a trapezoid, a rectangle, a third rectangle, a trapezoid, a second trapezoid, and a triangle at the end. All of those areas would have given us the same result of 6.3 inches. Here's one from the book. We're going to leave that to class time or a separate video. And one more example, finding the distance traveled when velocity varies. Okay, so now a particle starts at x equals 0 and moves along the x-axis with velocity function v of t equals t squared for time t greater than or equal to 0. Where is the particle at t equals 3? So let's pause and understand the question. We have a moving particle. It's on the x-axis. It starts at x equals 0. So here's 0. This is the x-axis. Its velocity function is v of t equals t squared. So that means the velocity is always positive. I don't have to worry about the particle moving backward. We're wondering where the particle is at time equals 3. So whether that's seconds or hours or milliseconds, as long as we've had 3 units of time, where is this particle now? So what we're trying to do here is get an accumulation of the distance traveled. An accumulation of distance traveled by the particle. So how do we do that? We take a look at the velocity graph. It's already graphed for us below. And we want to find the area under the curve. So this is basically the same as saying find the area under the velocity curve. So if we do that, if we find the area under the velocity curve and we say, hey, this particle has moved 10 spaces, 15, 20 spaces, and we know that it started out at space 0 or at x equals 0, we just add the accumulated distance to where it began and we'll know where the particle was at time equals 3. But this is an irregular shape. It's not like the previous example of 2 triangles and a trapezoid, or 2 triangles and a rectangle. It's not a giant trapezoid. This is a curve on top. So there's going to be some work for us to do. And you can see in the graph below that we've already started to cut this into thin, narrow strips. And it looks to me like for every 1 time unit, we've got 4 separate strips. So this is like 1.25 here, 1.5, 1.75, and then 2. Yeah. So I think on the next slide, what we can do is kind of zoom in on one of those strips. Yes, here's the zoom in version of the strip from 0.5 to 0.75. So there's the strip right there that we're looking at over here on the right. So notice that there are a few different rectangles drawn in. There's one rectangle drawn in that uses a height equal to the y value on the left side of that subinterval. So essentially what's done here is we take a look where 0.5 is on the left side of the subinterval. We go up to the graph, and then that becomes the height of the rectangle. So that rectangular area would be a pretty big underestimation of the actual distance traveled or the area of this strip. So an underestimate. There's another one drawn in where we use 0.75, the right side, and we go up to the curve. That becomes the height and then over. But notice that this is kind of overestimating what the actual area is because there's all this area here. It's in white but outlined in red that we would be adding into an area, but really we want just the blue area, what's under the curve. And then lastly, there's another piece. It's from the middle. So right here, right in between 0.5 and 0.75, where we would find 0.625. And we go up to the curve there, and that becomes the height. So we're going to go over a little to the left, over a little to the right. And notice that while there's a little bit of an overestimation here, it's kind of counterbalanced with an underestimation here. And that one's probably going to get us the very best approximation because it's not all an over or all an underestimate. So maybe we'll use that type of method to find the height. And then the base of this rectangle from 0.5 to 0.75 is 0.25 or about 1/4. And then here in green is what we're going to use as the area. So let's get a new screen here and we can kind of start to put these together. And I'm going to create a table to start to organize our math and our areas. So let's do subintervals and at least do the first 4. So we have a subinterval from 0 to 1/4. Another one from 1/4 to 1/2. That's the second one. A third one from 1/2 to 3/4. And then the last one between 0 and 1 from 3/4 to 1. So we'll see what happens there, and then we can kind of wave our hand and use the textbook to find the rest of these areas. So now let's figure out where the midpoint is because that's what we're going to use for the height. So the midpoint between 0 and 1/4 is 1/8. That's where it occurs. Between 1/4 and 1/2, so that's really between 1/4 and 2/4. So that would be 3/8. And then between 1/2 and 3/4, that's going to be 5/8. There's the midpoint. And you can kind of see the pattern here. This one's going to be 7/8. So now the height. How do you get the height? Well, you take your midpoint and it goes back into the function. That's what the y value will be. So 1/8 squared is 1/64. And 3/8 squared is 9/64, and 25/64, and 49/64. There are your heights. And then finally, your areas. Remember that your areas here are rectangles with bases of 1/4 or 0.25. So essentially what we're doing here is we're taking the base times the height. The base of all of our rectangles are 1/4. And the height is given by the midpoint squared. That's the function. So here we go. The height of this one will be 1/64 times 1/4. That's 1/256. Then 1/4 times 9/64 will be 9/256. And then 25/256. And then 49/256. And we could continue this all the way on until we got to the very last subinterval, which would be from 2.75 until 3, and add all of these narrow strips together. I'm just going to put a dot, dot, dot there until finally the area is approximately 8.98. I'm going to say see page 278 in your text. So to finally answer the question, where is the particle at time equals 3? It started at x equals 0. It moved 8.98 spaces to the right, so to about right here, 8.98. And so where is it? It's at about space 9. So we're at the particle at t equals 3 is at about x equals 9 or about 8.98. And that's all we're gonna do for this video. I know it was a long one. Join me for video 2, where I promise I'll try to make things a little bit shorter.